All right, here we are looking at approximating the area under a curve today, and we're going to do this using what are called Riemann sums. Okay, so and we'll talk about the different Riemann sums, this LRAM, MRAM, and RRAM. But what we're basically doing is we're approximating the area under a curve using rectangles. So we're using what's called a rectangular approximation method, and that's where the word RAM comes from. Okay, at least in the calculus sense, that's where the word RAM comes from. So if I wanted to approximate the area under this curve on the left side here, I could draw from A to B over here, and I could create this rectangle, and we know that the area of a rectangle equals base times height. And so the area of this guy, the base of this guy, would be the distance from B to A. So we know that this would just be B minus A. So that would be my base, B minus A. And the height of this rectangle, if you look at this point right here, we're going to just assume that both of these are at the same height for now. But if we were to look at this, the height of this point over here on the right at B is going to be F of B. That's the height right there. So if I wanted to find the area of this rectangle, I could also use, if these were at the same height, I could also use A, and I could call this same height F of A right here. So either one of these heights are going to be either F of B or F of A. So my height is just the base, which is B minus A, times the height, which is F of B, or the Y value that's at that point right there. Okay? So when we talk about a left-hand approximations, okay, so let me scroll down just a little bit there. Oops, too far. So when we talk about left-hand approximations, what we're doing is we're looking at using rectangulars, and we're looking at using the left-hand point for our height. Okay, so what I'm going to do is this. I'm going to actually split this this graph in half. So I'm going to call this point C right here, and I'm going to create a rectangle, and I'm going to create it from this point here and so it would come straight across and then straight down right here, and then I'm going to create a second rectangle, and I'm going to use this point straight across to here. And so I'm going to look at two separate rectangles here. And remember, this is a left rectangular approximation. So what does that mean? That means we're using the height on the left side of the rectangle. Okay? So for instance, in this first rectangle, I know that the area inside this one is, or the base is going to be C minus A. And I know that the base in the second one is going to be B minus C. The height of the left side of this first triangle is F of A, and the height of this second triangle on the right hand side, the left hand height of this triangle is F of C. So the area of this thing would be the base, which is C minus A, times the height, which is F of A, so times F of A, plus the height of, or the base of the second triangle, excuse me, B minus C, times the height of the second rectangle, which is F of C. All right? So, and that's how we would find the area of that. Now we can do the same thing using what's called a right rectangular approximation. So on the graph below this one, I'm going to do the exact same thing. I'm going to draw the triangles. I'm going to split it in half with the C value in the middle. But this time, here we go. Let's get everything labeled here. So here's C. Here's my point. Okay. But this time, what we're going to do, notice the difference in the triangles. I keep saying triangles. In the rectangles. This time, my rectangle is drawn from here to here and down. And then the second one is going to be drawn, again, this is a right-hand approximation. So my height of my triangle is coming from the right side. So this second triangle has a height of F of B. And this first triangle from A to C actually has a height now of F of C. So again, the base is still c minus a on the left side, it's still b minus c on the right side, so that doesn't change. So the area would be the base on the left, c minus a, times the height of the right side of that rectangle, which is f of c, plus the base on the right side, b minus c, times the height on the right side of that rectangle, which is f of b. Okay, so that's a right-hand rectangular approximation. And then we have what's called a midpoint. Okay, so a midpoint essentially takes the triangle. So I'm gonna split it again. So here's my c value again. All right, but a midpoint sum uses literally the midpoint for the height of the rectangle. So this time my rectangle is going from here to here, and then the midpoint of the other rectangle is going to basically be like that. Now the base of the rectangle is still c minus a and b minus c, same as the other ones because the base didn't change. But now to figure out this height right here, I have to know how to figure that out. Well, that height is in between a and c. So the coordinate of that point would be, and we could do this a couple of different ways here, but if that's the midpoint, the way you find a midpoint is a plus c divided by 2. That's the midpoint there. If we did the same thing over here, this would be c plus b over 2, which means the height of that point. Okay, so again, this is going to be my height, and this is going to be my height, which means the height is going to be f of whatever that value is, a plus c over 2. All right, and the height on the right side is going to be f of c plus b over 2. Okay, so the area of this one would be area equals, and then again, the base is still the same, it's still c minus a, times f of a plus c over 2. That's the height of that rectangle, plus the base on the right side, which again is still b minus c, times the height of that midpoint, which is f of c plus b over 2. Okay, so we're going to do some examples using some numbers instead of just, different variables and things like that, but let's take a look at what we got going on here. Okay, so I've got a table here, and it says use the table below to approximate the area under the curve using 3 equal intervals and LREM, REM, and MREM. So LREM means a left-hand rectangular approximation method, so that's using the left-hand point. And so it does say a couple of things we want to pay attention to here. It does say 3 equal intervals. So I've got a lot more than that in my t-table, but that's okay because I can split those up. So my first interval is going to go from, what do we got here? We got 0 to 4, it looks like. Yep, we're going to go from 0 to 4. So we're going every 4 here. So there's my first interval. My second interval goes from 4 to 8. Okay, actually I should probably do it like this. So the first one's going to go from 0 to 4, and then we're going to go from 4 to 8, and then we're going to go from 8 to 12. Okay, so, and again, because this is we're going to start off with left hand. So because this is a left hand, I'm going to go to the furthest left hand point, and I'm going to draw a rectangle from 4 all the way over, or excuse me, from 0 all the way over to 4. So that's my first rectangle right there, using the left side right there as my height. All right. My second rectangle goes from 4 to 8. Now, if you look at where the point is at 4, this point is way down here. Okay, and it's going to go all the way over to 8. All right. So that's my second rectangle from 4 to 8. And then let's see, my last rectangle here is going to go from 8 to 12. So you can see that the point over here at 8 is this guy. That's my left-hand point, and it's going to go over to 12. So we're going to draw that one in. All right, and because these are left-hand end values, we're basically using the height of 4 for the first rectangle. We're going to be using the height of 2 for the second one, and we're going to be using the height of 8 for the third one. Okay, now if you were to kind of picture this graph in here, and I'm going to draw it real quick just so you can kind of see what it looks like. If you were to picture this graph, it's going something like this, and then back up and around, and not so great, but I mean, those rectangles really don't approximate the area very well. So the smaller the rectangles get, the skinnier the rectangles get, the better they'll approximate the area here. So we're going to go ahead and take this off just so it doesn't get in the way here. So if I'm using a left rectangular approximation method, okay, so we're going to go left side here. So this is LRAM. And I need area base times height. Okay, so my first, you can see that my first base is, in fact, all of the bases are 4 down here. You can see that by the way I've drawn the triangles, but you can also tell because of the intervals on the side of the T-chart here. The first interval went from 0 to 4, which left me a base of 4. The second interval went from 4 to 8, which left me a base of 4. And the third one went from 8 to 12, which left me a base of 4. So all the bases here are 4. Okay, so from 0 to 4, okay, that's our first one. We have the base, and I'll just write it up here first. Base times height equals area. So the base is 4. And again, from the second one, we went from 4 to 8. And the base is still 4 because these are 3 equal intervals. We saw that in the directions. The third one went from 8 to 12, so it also had a base of 4. All we need to do is figure out the different heights. So if I look at this first rectangle, the one on the left here, it has a height of 4. Well, how do I know that? Because if I look at the left-hand endpoint right here, it's at 0, 4. The 4 represents the height of that y value. So this would be 4 times 4, so that's going to be 16. The second rectangle has a height at 4. So notice the height there is 2. So 4 and 2 go together. That's the height of that red rectangle. So this one's 4 times 2. That's going to give me 8. And then the last one, 8 to 12. So at 8, notice the height of the rectangle is also 8. All right, and you can see that again on that blue rectangle. It has a height of 8 and a base of 4 right there. So the height is given by your y value. The base is given between the distance of the x values, and then you just add them all up. And so the area under the curve would be, what do we got here? 24 and 32. That's going to give 56 units squared. All right. And so again, this height is the height of the left side of rectangle. All right. Hopefully that makes sense. We're going to do a couple more here. We're going to look at, let's do a right one next. Okay. So I'm going to do a right one. I might need to shrink the page here if I can. Hang on a second. I think I need to shrink so I can get all this in here. Let me see if I can slide this just a little tiny bit. Oh boy, now I'm having problems here. Yeah, hang on. Let's see if I can just view. That's a little ways out, but that'll have to work. Okay. All right. So a little bit smaller here, but I think you'll get the idea here. So on my next one, we're going to do, we'll do RRAM. We'll do right side. So this is a right side rectangular approximation method. All right. We still have the same 3 intervals here. So we got the interval from 0 to 4. Okay, that's my first one. 0 to 4. We've still got the second one. I'll draw these in different colors from 4 to 8. So we're going to have that one, 4 to 8. So hopefully you can kind of already see that the bases are still the same on these guys. And then we've got the last one, which goes from 8 to 12. So the intervals didn't change, but watch what happens as we draw these rectangles. Okay, I'm actually going to start, since I'm in blue, I'm going to start. This time, because it's an R-rim, I go to the side at 12. Okay, so my rectangle this time is going to go all the way up to 12 on the right side, just like that, and it's going to come back to 8. Okay, so because I'm doing a right side approximation, that means I'm going to use the point on the right side, and that's this guy right up here at the top. Let's see, we'll go back to the green. So we're going from 0 to 4, and we're using the right side approximation. So here's the point right here at 4, 2. That's the right hand point of that interval. So we'll be using that height. And then in the middle, we're going to go right hand approximation. That's this point right here for the middle interval. And so that's what that rectangle would look like on that side. Now, I'm going to draw this again just so you can see, because again, all this is approximation. So if you look at the curve again coming up, this time you can kind of see that that curve is going to overestimate the area on this particular curve here. Okay, so hopefully you can kind of see that. Let's go ahead and do the math here and see what we got. So we have base, which again, I think it's pretty obvious that all the bases, so base times height, all of these are 4, 4, and 4. And then what else we got here? We got height. So this time we're using the height on the right side here. So again, I'm using the height, and you can see the height from the green rectangle. Its height is 2. You can also see that in the chart right here, because at 4 the y value is 2. So that's my height. So that's going to give me area of 8. And then going to the second rectangle, the red one, we're using the height at 8 on the right side. So the height of that rectangle is going to be 8. And then in the interval from 8 to 12, we're using the height at 12. So that one's going to be 22. So we got 32 there. We got 88 here. And so our total area here is 128 units squared. Okay, it's total area under the curve using that estimate. Now you can see that those two estimates, 128 versus 56, those are pretty far off from each other. Okay, and then we have a third one called MRAM. That's where we use the midpoint value. All right, so don't worry about this black line in the t-table. I don't know where that came from. So it doesn't change the intervals. We're still going to go from 0 to 4. So I'm gonna draw, but this time I got to kind of think about what's in the middle of 0 and 4. Well, this point right here, that's right in the middle. So my rectangle for the first one is going to look just like that, because now I'm looking at using the midpoint value. So the midpoint between 0 and 4 is 2. Between 4 and 8, I have a midpoint value at 6 right here. So I would draw my rectangle at that midpoint value. The height of that rectangle is going to be at that midpoint value. And then finally, from 8 to 12, I have this midpoint value at 10. So I'm going to draw this one at 10 like this. Okay. Now, if I didn't have those midpoint values, I wouldn't be able to do a midpoint sum. But because I do, I can go ahead and do a midpoint sum here. All right. So again, the bases don't change. So this is called MRAM, midpoint rectangular approximation method. So the base is still 4 on all three of these guys. So 4, 4, and 4 times the height. And the height on the green one, you can see I'm going to mark all the heights in the t-chart here because I'm using midpoint. So I'm using the point at 2. The height is 2. I'm using the point at 6, so at 6 the height is 4, and I'm using 10, and the height at 10 is 14. So that's going to give us 8 and 16, which is 24. 24 and 56 is going to give us an area of 70 units squared. Or did I add that up wrong? Maybe it's 80. It's 56. Yeah, it's 80 units squared. Okay, so that's a visual of how you do that. Now, that's pretty easy to do if we have nice little intervals and we can see all this stuff. Let's take a look at the next example and see what we got going on here. Okay, and I think I may try and go back to normal size here. See if we can get those a little bit bigger here. Okay, so what does it say up here? It says find the area of the curve, and the graph is y equals 3x squared. Okay, so I'm just going to put this over here so I can see it a little better. This is going to be y equals 3x squared. So we're finding the area of the curve bounded by y equals 3x squared, and the x-axis from x equals 0 to x equals 2 using n equals 4. This denotes the number of rectangles, so we want to use 4 rectangles. And so basically if I'm going from 0 to 2, let's look at that area under there. So I'm going to be going from, here's 2 out here on the right side. Okay, so what I'm attempting to do here is find the area in this space right here. All right, so you kind of get the idea in there what we're looking at in there. Okay, I want to find that area in there, and I'm supposed to use 4 rectangles. Okay, I've got my equation. Now this time you can hopefully kind of understand why I have an equation, because some of these rectangles are not going to be obvious in their height. So the first thing I want to do is I want to look at the size of the interval. The size of my interval is 2 units. Okay, so I need 4 intervals, and these are all going to be the same. 4 intervals. And so I need to figure out how wide to make these. Well, again, I need the distance of the entire interval, so that's going to be 2 minus 0, divided by the number of intervals that I want, which is 4. So that means that each interval should be a half a unit. Okay, that should make sense there, I hope. And so I'm going to split this up. I'm going to come over here and I'm going to try and draw the best that I can. So that's going to be one of my intervals right there. This is going to be 2 of the intervals right there. And I'm going to have to kind of guess at this third one here. So this is my 3rd and 4th interval right there. Now again, you can see that because they're even, they all have a base of 1/2. Okay, so all bases equal 1/2. And this doesn't matter if we do left-hand approximation, right-hand approximation, or midpoint approximation. All the bases are the same. What changes now, again, is the heights. So let's start off, and we're going to do an LRAM here. So we'll do LRAM. And again, my equation here, I'm actually going to bring it down because I'm going to scroll up just a little bit more. Y equals 3x squared. And there's a reason we need that this time. So there we go. So we scroll up a little bit here. So we're going to be looking at the interval from 0 to 1/2. Then we're going to look at 1/2 to 1. And we're going to look at the interval from 1 to 1.5. All right, or 3/2. Maybe 3/2 would be better. It will in the future here, trust me. And then we're going to look at the interval from 3/2 to 2. And we're going to do LRAM. LRAM means that we're going to use the point from the left side of the interval. So think about this first one here. If I look at the base, okay, so again, this is base times height. All right, so if I look at the base, this first one, if I use this left-hand point, if I try and draw a triangle there, it looks like that. It's got no base. Well, it's got a base, but it has no height. And that's because my point is down here at 0. So again, the base, all of these guys are going to be a half. But that very first rectangle, because I'm using the left-hand point for approximation, it has no height. All right? If I go to the second rectangle and I take a look at the second rectangle and I use the left-hand point right here. So I need that point. Here's my second rectangle right there. Well, I need to know how high that is. So it looks to me like it's 1 unit high according to the graph. But how do I know that without plugging it into my function? So what I'm going to do is, on the first rectangle, I used 0. On the second rectangle for the height, I'm using a half. On the third rectangle, I'm going to use 1. And on the fourth rectangle, I'm going to use 3 halves. All right, that's going to be the height of each one of these. I'll actually finish drawing these out. My third rectangle, there's the height right there at that point. My fourth rectangle looks like it's about right here. So there's the point, and you can see the 4 rectangles in there now. All right. So in order for me to figure out the height of this second one, I've got to plug in a half to the function here. Remember, it's the y value that we're looking for right there. Okay. So if I plug in, I get, what do we got here? Well, we'll call this, we're going to make this a little bit different. This y equals, we're going to call this f of x. Might make a little more sense. So what I need here is I need f of 1/2. Where'd the 1/2 come from? That's the x value on the left side. Okay, so we'll call this x1. This x2 is the value on the right side. So the next one would be 1/2 times f of the left-hand x value. That's going to be f of 1. And the last one's going to be f of 3 halves. That's the height of that rectangle. So we got to do a little bit of work here. Obviously, this first one's going to be 0. Okay, so I know that area on this first one is going to be 0. Now the second one, I need to know what f of 1/2 is. All right, so f of 1/2, if we plug that into the function here, we've got our 1/2 out in front, and then we plug in times 3 times 1/2 squared. Okay, so a half squared is a fourth times a half is an eighth, and an eighth times 3 is 3/8. So the area of that second rectangle is 3/8. We do the next one. We got our base of a half. We plug in 1 for x. That's times 3 times 1 squared. So this piece here, again, what we're looking at here, hopefully you can see this. This is my height right here. Okay, that section is the height. So this is going to be 3 times 1 is 3. This is going to be 3 halves. And my next one is going to be 1/2 times 3 times 3 halves squared. And so that's going to be 9/4. 9/4 times 3 is 27/4. And 27/4 times a half is 27/8. All right. So there is the area of the third one. I need to add all these together. If you add all these together, and you can take my word for it, or you can sit there and add them on your own, this is 42/8 units squared. Not sure what happened to my 8 down there, but this would be the area underneath that curve using those 4 rectangles as approximations. All right. We're going to do RRAM on the next side. Okay. So let me slide over a little bit here. Okay. And we'll do some RRAM on this side. RRAM means we're using, again, the same intervals. Okay. So I'm going to draw these guys out here again. So we're using this interval. We're using this interval. Again, this interval. And here's the end of the entire interval. Okay. So this is RRAM. What does RRAM mean? RRAM means that we're using the right-hand point to approximate our height of our rectangles. So RRAM. Okay, let's draw. So this is the right-hand point of my first rectangle, so I'm going to draw there. This is the right-hand point of my second rectangle, so I'm going to draw here. So that rectangle, you can see, kind of sticks out a little bit. This is the right hand point of my third rectangle, so I would draw this direction. And my fourth rectangle looks like it's about up in here, so this would be my fourth rectangle and its height right there. Okay, so you can obviously see that this estimation is going to be well over the area under that curve, but my first estimation was under because the rectangles were all underneath the curve. And so, you know, we could talk more about that, but we'll leave it alone for now. So we need base, which we know all the bases are a half, so that's cool. 1/2, 1/2, 1/2, and 1/2. And then we need a height. So again, I'm going to go back over to, well, actually, let me do this. I'll write these out. We're using the same intervals here. So this is the interval from 0 to 1/2. And this would be the interval from 1/2 to 1. This is going to be the interval from 1 to 3/2. And this is going to be the interval from 3/2 to 2. So because this is a right rectangular approximation, we're now using the x values on the right side to create our rectangles, which means when I go to find the height here, I'm going to find the height as f of 1/2. So I'm using the right hand x value for the height of that first rectangle. I'm going to multiply the second one times f of 1. I'm going to multiply the third one times f of 3/2. And I'm going to multiply the last one times f of 2. Now, I don't have to do a whole lot of work here again because I've already done some of this on the left side. So I already know what f of 1/2 is. Well, I didn't actually do all the work, did I? Well, I guess we're going to have to do it again then because I didn't write out answers on the other side. So I've got 1/2 times f of 1/2, and we kind of did that over here. This was, oh no, we did do it. We did get it all over here. We did have enough. So that area of that one in the second one down on the left side here was 3/8. So if I do 1/2 times f of 1/2, this is 3/8. If I do 1/2 times f of 1, which we did on the left side, that's 3/2. If we do 1/2 times f of 3/2, that was 27/8. So the only thing we have to really do is f of 2, and that one's pretty easy. This is 1/2 times 3 times 2 squared. 2 squared is 4. 4 times 3 is 12, and half of 12 is 6. So if we add all these guys together, we get the area equals 90 over 8 units squared. Okay? And yeah, you could simplify that if you wanted to, but all right. So that's RRAM. Again, that's using the right-hand approximation. And then we're going to do MRAM with the same one. Okay, so we'll take a look at MRAM if I can find my cursor here. There we go. All right. So this one's going to be MRAM. All right, so here we go. Let's see. So we're going to have a little bit more work to do on this one. So we're going to do MRAM here. MRAM's a little more difficult because we have to look at the midpoints of each one of those. So I'm going to draw again. We're going to start out by drawing our 4 values here. So I'm just cutting up into the intervals that we were given. All right. And so there's my 4 intervals. But here's the tricky part about this. I'll do this in a different color. I need the midpoints of each of those intervals. Okay, the midpoints, which means, now did the base change on these guys? It didn't, did it? So let me actually do this. MRAM, base. The base is still 1/2, 1/2, 1/2, and 1/2. But what I need now is I need the midpoint of that interval. So my first interval is 0 to 1/2. My second interval again is 1/2 to 1. My third interval is 1 to 3 halves. And my fourth interval, again, is 3 halves to 2. Now, if I draw those over here on the left side, you can kind of see this gets a little bit tricky here because here's a fourth over here. So trying to look at that little tiny rectangle right there, I mean, this just gets ugly. Okay, same thing with the next one. If I go halfway between these guys, it looks like I'm somewhere in this area. So I'm trying to draw these little rectangles and I really don't know where I'm drawing them. It's just really hard to see. And we could continue to do that, and you know, we're still going to have to do some math here at some point. So to find the height of these guys, you remember when we talked about MRAM is the midpoint of this interval. Okay, well, again, how do I find a midpoint? So the height, okay, so I'm going to talk about it in terms of this first rectangle. This first rectangle is the midpoint between 0 and a half. Well, how do you find a midpoint? You add up the interval and divide it by 2. So this would be 1/2 times the let me see here, we need the height. Oh, this is gonna, I need the midpoint first. Let me do this. Midpoint. All right, so I need to know exactly what the midpoint is. All right, so this is gonna be 0 plus 1/2 divided by divided by 2, okay, because we're splitting the interval in half. So this is going to equal 1/2 divided by 2, which is 1/4. Now that should make sense because what's right in the middle of 0 and 1/2? That's 1/4, okay? But this isn't my height. This is the x value. This is the midpoint x value that I now need to use to find the height. The height is the y value when x is equal to 1/4. So the height is f of 1/4. Okay? So if we plug in 1/4, and again, I'm going to bring down my function here. This was f of x equals 3 times x squared. So if I plug a 1/4 into there, I get a 1/4 squared, which is a 16th, and a 16th times 3 is 3/16. So midpoints take a little more. Now, if you look at what you have now, I've got the base on the left here, which is 1/2. I've got the height, which is 3/16. So the area of that first one now would be 1/2 times 3/16, which is 3/32. And we continue on from there. Let me get a little darker color here. So I need the midpoint of the next interval. Now again, you can probably guess at this midpoint. You probably already know that it's 3/4. But sometimes you're not going to know, and you're going to need to make sure that you can do this algebraically. So this midpoint is going to be 1/2 plus 1 divided by 2. So 1/2 plus 1 is 3 halves. 3 halves divided by 2 is 3/4. That should make sense there. So the height of this is going to be f of 3/4. What's the y value when x is equal to 3/4? And again, we can plug that in. We get 3/4 times 3/4, which is 9/16, and 9/16 times 3 is 27/16. All right, that's the height. All right, I multiply the height times the base, and we get 27/32. That's your second one. Third one. Here we go again. We need the length of the interval. That's going to be 1 plus 3 halves divided by 2. So that's 2 halves plus 3 halves. That's 5 halves divided by 2 is 5/4. Hopefully, again, that makes sense because 5/4 is directly in between 1 and 1.5. So I need f of 5/4. So I'm going to plug in 5/4 to my function again. That's going to be 25/16 times 3, which is 75/16. That's the height times the base, which was 1/2, and that's 150/16. A little tedious here, huh? All right. Did I do that one right? No, I didn't do that one right. I multiplied the top, not the bottom. I knew something was wrong there. So this is 75. I don't want the equal sign there. This is 75 30-seconds. That sounds better, doesn't it? Okay, and finally our last one here. So we'll go and do 3 halves plus 2, which is really 4 halves. So that's 7 halves divided by 2, which is 7/4. Then we'll find f of 7/4. And if we do some math here, 7/4 squared is 49/4 times 3. That's going to be 147 over 16. And then we would multiply that by a half, and we get 147 over 32. Now the nice thing is, at least all of our fractions came out with 32 on the bottom. We add all these guys up and we get an area of 252 30-seconds units squared. And I really don't care to simplify that fraction. You can if you want to. All right, fun stuff, huh? All right, looks like we got 1 page left here. Let's take a look. All right, it says to approximate the area, oops, a little too far, approximate the area of the curve bounded by y equals x cubed and the x-axis from x equals -2 to 2 using 4 intervals, n equals 4 using Riemann sums. Okay, and so, all right, so we're going from -2 to 2, and so I'm going to set up my intervals over here. So we've got, we need to find the distance for each of these. If you're going -2 to 2, that's pretty easy to see, but I can always find the length of the interval. So what do we going to call this? Length of interval. So this is going to be 2 minus -2 divided by 4. So that's 4 over 4. So each of these intervals has a distance of 1, which means my first interval is going to go from -2 to -1. My second interval is going to go -1 to 0. My third interval is going to go 0 to 1. And my fourth interval is going to go 1 to 2. All right. Okay, so what's the base? Always start with that. The base should be obvious on all these guys. It's going to be 1, 1, 1, and 1. That was easy. The problem is the height's not the easy one here. So now we need a height. In order to find a height, I need the y value. Okay, so this is LRAM. So the height is the y value from the left side. Okay, so again, I'm going to highlight these. This is, well, I don't think I want to, because I'm going to be using the values in the intervals for all 3 of these guys. So I need the y value from the left side. Well, the left side, you can see, I mean, this is the left side of the interval, this is the right side of the interval, so we're using all of these x values down the left side. All right, how do I find the height? I need to plug it into my function. Okay, so if you look at this, we plug in -2 for y equals x cubed, and so that's going to be, we'll just do this the same way. So this is f of -2, and obviously you can do that in your head. -2 cubed is -8. Okay, and so the area here, remember, we're not talking about an integral, we're actually talking about area here. So the area of this particular section is going to be 1 times +8. Okay, we go to the next section. We've got a height, so we're using the left hand point. We need to know what f of -1 is. Well, again, if you plug that in, -1 cubed is -1. -1 times 1 is -1, but we want this to be positive, so we're going to do +1 here. Next one, we're using the left endpoint, so this is f of 0. That's pretty obvious. That's going to equal 0, which is going to leave us with 0 area. Kind of weird, huh? And the last one, we need f of 1, and 1 cubed is 1, so 1 times 1 is also 1. If you add all of these together, we got 8, 9, we have 10 units squared for the area there. Okay, that's using LREM. Let's do the same thing again. This time we're going to use RREM. So now we're using the right-hand x values. Okay, the base did not change here. The base stays the same. This is 1, this is 1, this is 1, this is 1. But now our height is from the right side. So instead of using -2, I need a height of f of -1. Well, guess what? We did that in the previous one. That was -1. So the area here is going to be 1 times -1, which is -1. We make it positive. The next one's going to be f of the right side of the interval. The right side is 0. And so that's going to be 0. So an area of 0. The next one is going to be the right-hand side. So that's going to be f of 1, which we already did. That's 1. So that gives me an area of 1. And the last one is 2 on the right side. So that's f of 2. And 2 cubed is 8. And look at that. We get the exact same area that we did before, 10 units squared. Interesting, isn't it? If you know what the graph of y equals x cubed looked like, you'll know why that's happening. All right, last one. All right, MRAM. So now we need a base. Okay, did our base change? Absolutely not. It's still 1, still 1, still 1, still 1. Did the height change? Yes, it did. Now, this one should be a little pretty straightforward to find the height. Okay, but before I find the height, I need the midpoint. Okay, so I need to know what the midpoint is. So I'm just going to call this midpoint. All right, so in between -2 and -1 is -3/2. -3/2. My height is the y value f of -3/2. So you got to be careful here. All right, so my height on this one, if you plug that into the function, it's -3/2 times -3/2 times -3/2. That equals -27/8. But the base is 1, so the area is just +27/8. There's your first one. The second one, what's in between -1 and 0? That would be -1/2. I plug -1/2 in, and I do f of -1/2. And that turns out to be -1/8. So the area is +1/8. I go to the next one, I do the same thing. The next one is +1/2 as the midpoint. Well, guess what? +1/2 and -1/2 give the same value, only this one's positive, and so this guy turns out to be 1/8 for the area again. And for the last one, we're going to do +3/2 for the midpoint. So f of +3/2, we've essentially already done that. The very first one, this is +27/8. All right, and then we just add all these guys together, and we get a total here of 56/8. And you could simplify that. Oh, that one simplifies out very nicely, doesn't it? 7 units squared. All right. Okay. So I would turn off the video and maybe try the next one on your own. Okay. You're given a table on this one, and this time we're using the use the table below to approximate. Now this time it doesn't say we're approximating area. It says we're approximating the integral from 0 to 42 f of x dx using LREM and RREM. So we're not doing MREM here. And it says using 6 intervals. If you look at your t-table, there are 6 intervals already there for you. Okay, the key here is it doesn't say 6 even intervals. All right, so you just use the intervals that you're given. So I would try it. I would turn it off, write down each interval just like I did, figure out what the base is for each interval, figure out what the height is for each interval, and then figure out the area. Okay, so I'm going to start off with LREM here. All right, so LREM. And my intervals aren't going to change here, so I'm going to write them down one time here. Okay, so my intervals. Now, if you were doing this on an AP test, you might not write down the intervals because they're fairly obvious here, I think. My first one's going to be from x equals 0 to x equals 5. My second one's going to go from 5 to 12. My third interval is going to go from 12 to 14. The next interval is going to go from 14 to 21. And one of the things you can see is that these intervals now they're not the same length. So when I go from 21 to 38, that one's just spread it way out right there. Okay, they don't have to be the same length unless the problem says they have to be the same length. The last one goes from 38 to 42. Now, why is that important? Because it changes the bases on your problems here. So doing LRAM here, we would have a base. So I'm going to start by listing all the bases. 0 to 5 gives me a base of 5. 5 to 12 gives me a base of 7. 12 to 14 is 2. 14 to 21 is 7. 21 to 38, holy cow, that's 17. And 28 to 42. So that's the base. Now the base won't change going from LRAM to RRAM, so I don't have to worry about that. But the height will change. So times height. The height, and what I need is I need the height on the left side of the interval 0 to 5. So the height is going to be 7 on the left side of that interval. So that's going to give me an area of 35. The next interval from 5 to 12, I need the height on the side of 5. That height is 6. The y value is 6. So that's times 6. That's 42. The next one, the height at 12 is 15. So that's going to be 30. The next interval, I need the height at 14, which is 10. That equals 70. The height on the next one at 21 is 16. So 17 times 16, I'm going to have to cheat here, that's 272. And then the last one, the height at 38 is 8. So that's 32. Add all these guys up, we get 481 units squared. Now, you'll notice it says we are approximating the integral. None of these areas came out negative, but if they would have come out negative, we would have left them negative because we are approximating an integral. Okay? So just kind of keep that one in mind there. Let's do RRAM. So right side, rectangular approximation method. Now again, I'm just going to write the bases in here just so you can see the bases are always going to be the same. 5, 7, 2, 7, 17, and 4. But again, if I was doing this on a test, I might skip that part and just go straight to height. So now I need the height on the interval from 0 to 5 on the right side. So again, I go to 5 and I look at the y value at 5. That's going to be 6. So 5 times 6, this is going to give me an area of 30. I go to the value at 7 on the next interval, on the second interval. My base is 7. I need the height at 12 this time. So that height is 15. So that's going to be 105. I go to my next interval from 12 to 14. I need the height at 14. That's going to be 10. So that's 20. 2 times 10. The next interval, I need the height at 21, so that's 16. I'm going to have to cheat on this one. I don't know what this is. This is 112. The next interval is 21 to 38. I need the height at 38, so that's 8. And 17 times 8 is 136. And then my last one, I need the height at 42. The height at 42 is 19. All right, and that's 76. You add all those guys up, you get 479 units squared. Pretty close to the other one, okay? Pretty darn close to the other one. Let's see what this question says here. Why did we not do the table by MRAM? Well, think about it for a minute. Think about what's in the table. In order to do MREM, I need some midpoint values. And the problem here is I don't know what's in the middle of 7 and 6. I can't assume that it's 6.5 is the middle value. I'm not allowed to do that. I don't know what I'm literally missing. I know what the middle X value is, but I don't know what the middle Y value is. Okay? So because I don't know the midpoint, I could figure out the midpoint X values. All right? This is because we don't know the midpoint Y values. We could figure out the midpoint X values, but we're never going to figure out the midpoint Y values. There's your first assignment. Have fun. That wasn't so bad, huh?